In this example, we will examine projectile motion. A ball is thrown off the side of a 200-foot cliff with an initial speed, v0, of 100 feet per second at an angle theta, 30 degrees relative to the horizontal. How high will the ball travel vertically, d, before reaching its maximum height? How much time, td, will elapse until the ball reaches its maximum height? How far will the ball travel horizontally, L, before striking the ground? How much time, TL, will elapse until the ball strikes the ground? At 1 second and 2.5 seconds after the ball is released, what are the normal and tangential components of the ball's acceleration, AN and AT? What is the radius of curvature of the ball's path, ρ? What is the time rate of change of the ball's speed, v dot? We will neglect air friction in this problem. First, write out the equations that govern the position and velocity of the ball as a function of time. The initial position of the ball, x0 and y0, depend on the location of the origin. If the origin is placed at the starting position of the ball, x0 and y0 become 0. The components of the initial velocity, vx0 and vy0, are obtained from v0 and theta using trigonometry. Plug in the values of x0, y0, vx0, and vy0 into the expression for x, y, vx, and vy. Now time is the only unknown variable on the right-hand side of the projectile motion equations. In order to calculate d and td, we start with the equation describing the y-coordinate of the ball. When the ball reaches a height d, the time will be td. We have one equation and two unknowns, d and td. We also know that the ball's speed in the y direction at time td will be 0. Now we have two equations, two unknowns, and can solve for d and td. The ball will travel 38.2 feet vertically in 1.55 seconds before falling back down to Earth. In order to calculate L and TL, we start with the equation describing the x-coordinate of the ball. When the ball travels a horizontal distance L, the time will be TL. We have one equation and two unknowns, L and TL. We also know that the ball will have fallen a vertical distance -h at time TL. Now we have two equations, two unknowns, and can solve for L and TL. The ball will travel 468 feet horizontally in 5.40 seconds before striking the ground. The ball is accelerated in the negative y direction at a constant rate g. We can relate the acceleration in the rectangular coordinate system to the acceleration in the pathline coordinate system using geometry. The positive direction for the t-coordinate is in the direction of the velocity vector. The positive direction for the n-coordinate is pointed toward the center of curvature. At all points along the path, the normal component of the acceleration vector points toward the center of curvature and is oriented 90 degrees relative to the velocity vector. If the angle between the velocity vector and the horizontal is phi, then the angle between the normal acceleration component and the acceleration vector also is phi. At all points along the path, the tangential component of the acceleration vector is parallel to the velocity vector. As the ball travels upward, as shown in the diagram, the tangential acceleration component will be negative. When the ball travels downward, the tangential acceleration component will be positive. The normal acceleration component is g times cosine phi. Cosine phi is equal to the x component of the velocity vector divided by the magnitude of the velocity. The magnitude of the velocity vector is the square root of the sum of the squares of the vector's components. Plugging in expressions for Vx and Vy, we obtain an expression for the normal acceleration component as a function of time and the known quantities. The tangential component of the acceleration vector is negative g times sine phi. The negative sign appears because the tangential acceleration component is pointed in the negative t direction as the ball travels upward. When the ball travels downward, sine phi will be negative, which makes the tangential acceleration component positive. Sine phi is equal to the y component of the velocity vector divided by the magnitude of the velocity. Plugging in expressions for Vx and Vy, we now have an expression for the tangential acceleration component as a function of time and known quantities. The radius of curvature and time rate of change of the ball's speed are obtained using the general equations for the normal and tangential acceleration components. The normal acceleration component is equal to v squared divided by rho. Solving for rho and plugging in the expressions for Vx and Vy, we obtain an expression for the radius of curvature as a function of time. The time rate of change of the ball's speed is equal to the tangential acceleration component. As we found out earlier, the ball begins its descent at 1.55 seconds. This means the ball is traveling upward at 1 second. The normal acceleration component is 31.5 feet per second squared. The radius of curvature is 248 feet. Both the tangential acceleration component and v dot are negative 6.48 feet per second squared. At 2.5 seconds, the ball is traveling downward. The normal acceleration component is 30.4 feet per second squared. The radius of curvature is 278 feet. And finally, both the tangential acceleration component and v dot are 10.7 feet per second squared.